I know that it is a day late, but that's all right. So I just want to say some things about our, or at least one of our favorite numbers. So, as you guys know, pi is defined to be the ratio of a circle's circumference to its diameter, at least in Euclidean geometry. So that's a pretty simple definition of what pi is, but it has some amazingly interesting properties. So first, the way people approximated pi was by taking regular polygons, and so they would put one regular polygon, inscribe it inside the circle, and one regular polygon, circumscribe it around the circle. And by estimating either the shape's area or the shape's perimeter, you could get an approximation for pi using either circumference is 2 pi r or area is pi r squared. So for example, if you have a square, and you can place pi between 2 times the square root of 2 and 4. And then if you use if you use polygons with more and more sides, you can get a more and more accurate estimate of pi. So for example, for a regular hexagon, I can sandwich pi between 3 and 2 times the square root of 3, which is roughly 3.46. And as you use more and more and more sides, you can get a more and more accurate estimate. So for example, Archimedes made the first well-known, at least fairly accurate estimate of pi. He used a 96-sided polygon by starting with the hexagon and dividing the angle by 2 again and again and again. And he got pi down roughly to about 7 decimal places. So one of the interesting things about pi is that it's irrational, meaning that it cannot be expressed as a ratio of 2 integers. This eluded mathematicians for a very long time. People believed it but could not prove it until the 18th century, and Heinrich Lambert finally proved it then. And pi is additionally transcendental, which means that it cannot be the root of a polynomial with all integer coefficients. So for instance, the square root of 2 is irrational but not transcendental, because I can say x squared minus 2 equals 0, and now the square root of 2 is a root. But pi cannot be expressed in such a manner. And this was proved by Ferdinand von Lindemann, and the way in which he proved it was fairly interesting, and it's something we'll get back to later. One consequence of this is that this problem, squaring the circle, a classic problem in geometry that stumped mathematicians for many centuries, is impossible. Squaring the circle is creating a circle with the same area as a square using only a straight edge and compass, and it was proven to be impossible. Now, for a very long time, until relatively recently, just a few centuries ago, the approximations of pi were just dominated by taking polygons and using more and more and more sides. However, soon enough, mathematicians, with the development of calculus, started using infinite series, to approximate pi. And then these led to very accurate and very rapid methods of calculating pi. So for example, Ramanujan found many formulas for pi in terms of an infinite series that converge very quickly. So for instance, they may give you, with every single term, they may give you a new decimal place, which is very, very fast. And some of the modifications of Ramanujan's series are still used today by supercomputers to calculate pi to trillions of decimal places. Here is one of them. 1 over pi equals this stuff. I'm not going to read it all out. This is often considered one of the ugliest formulas in math. Fun fact. Now, currently, in October 2014, a calculation of pi was made to 13.3 trillion decimal places. In fact, it wasn't even done by a supercomputer. It was done by a home computer, but it took about 208 days. And since 2010, all of their record computations have actually been performed using the same program. And it was developed by Alexander Yi initially as a high school project, but ultimately it went much farther than that. So now I want to talk about some of the cool applications of pi. Now, we all know that pi, anything that has to do anything with circles, pi will show up. But there are some things that people don't know where pi shows up, and you might not expect them. So for example, in physics and engineering, you'll see them in some equations where you might not expect them. For example, in Heisenberg's uncertainty principle, this principle states that the uncertainty in the position when measuring a particle and the uncertainty in the momentum, when multiplied together, must be at least Planck's constant over 4 pi. And what this means is that you can never measure position and momentum together too precisely. And you can also see Einstein's field equation. It's very important in understanding our universe, as well as one formula from structural engineering, which tells you roughly how much force can be placed on a long axial rod without it fracturing or being damaged. Another thing that a lot of people don't expect is pi showing up in number theory, which it seems very counterintuitive to a lot of people, especially when you think about the fact that number theory tends to deal only with integers, and we already said that pi cannot really be connected to integers in any nice way, at least at first glance. And you can see that, but this sum, this very intriguing sum, 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared plus blah blah blah, it actually equals pi squared over 6. And you see a similar one for the fourth powers. And an interesting consequence of that first equation is that if you take two integers, then the probability that they will be relatively prime is 6 over pi squared. And it's actually a direct consequence of the fact that 1 over 1 squared plus 1 over 2 squared plus blah 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 is pi squared over 6. And another interesting way of obtaining pi is using something called the Wallace product. And so you can see that pi over 2 equals that product on the bottom, 2 over 1 times 2 over 3 times 4 over 3 times 4 over pi times and so on. And the way you get that, for those of you who are familiar with calculus, I put the equation on the top. So you guys know that the sine function equals 0 at all of the multiples of pi. So 0, pi, 2 pi, 3 pi, and so on. And then negative pi, negative 2 pi, negative 3 pi, and so on. And so Euler found out that, now proving this is a much more difficult task, but it is true that even if you have infinitely many roots, you can treat a function as a polynomial with the corresponding roots. So you can write sine x over x equals 1 plus x over pi times 1 minus x over pi, which gives you that first factor, and then 1 plus x over 2 pi times 1 minus x over 2 pi, which gives you the second factor, and so on. And then all you need to do is plug in x equals pi over 2, and the formula will pop right out. And pi also shows up in perhaps something that is a little more applicable to everyday life. So the parent function for the normal distribution is this function, e to the negative x squared. It turns out that if you integrate this from negative infinity to infinity, you get the square root of pi. This is called the Gaussian integral. And again, it's something that's very surprising, and it's one of the very interesting connections between e and pi. And what this means is that when you write out the probability density function for the normal distribution, you do get a pi in there. And the normal distribution is used everywhere. If you take a bunch of samples of pretty much anything that exists in our normal world and not having some extremely strange properties, and you take enough samples, they will eventually form a normal distribution. And so the normal distribution is used everywhere in life, and something that can be used basically in everyday life. And of course, one simply cannot talk about pi without talking about Euler's famous identity. So it turns out that the e to the power ix actually equals cosine x plus I sine x. Arguably one of the most important theorems in all of mathematics. And when you plug in the value pi, you get this equation, e to the power I pi plus 1 equals 0. Often considered the most beautiful equation in all of mathematics because it includes arguably 5 of the most important mathematical constants, 0, 1, pi, e, and I, along with each of the first 3 hyperoperations exactly once, meaning addition exactly once, multiplication exactly once, and exponentiation exactly once. And it even has 0 on one side of the equation, which is often considered nice or a standard form. So this is arguably one of the most beautiful equations in mathematics in stark contrast to the ugly equation we saw earlier for computing 1 over pi. And an interesting thing is, because e to the power I pi is -1, that can actually be used to prove that that pi is transcendental. Because e to the power, it was proven by the same person that e to the power any algebraic number must be transcendental. And so, if e to the power I pi is -1, which is clearly not transcendental, then I pi must be transcendental, which means pi must be as well. And now, pi actually appears in a lot of places in popular culture. And so, for instance, you can see it in a lot of cartoons. You can see it in some books. The person who named himself Pi as a nickname in this book to avoid being made fun of by his friends actually did reference it once, that his name's connection to the mathematical constant pi. It makes many appearances in The Simpsons and some other TV shows. And there's something I only found out today, there's even a cologne called Pi. Unfortunately, it's not pie flavored in any way, and it does not cost $3.14. It costs about $60, which is about 19 times as much. So, but if you want to get some, then you should consider it. All right, so one of the funny incidents about pi is the Indiana Pi Bill, which is something that mathematicians love to make fun of. So in 1897, Edward Goodwin, in an attempt to square the circle, which had recently been proved impossible, and he attempted to have a law passed that would allow him to square the circle. And what that law was going to do, it was actually going to effectively redefine the values of pi in the square root of 2. So if you look at that picture over there, you can see that the radius of the circle is 5, the diameter is 10, and then that segment is 7. So you could and then the arc of that circle, 1/4 of the circle is 8. So he would effectively be redefining pi to 3.2. And he would effectively be defining the square root of 2 either to 10/7 or 7/5. And in fact, this bill actually passed through the House of Representatives. But then, this math professor right here, Professor Waldo, he actually taught the Senate math before they voted on the bill. And so when it reached the Senate, they tossed it out. And so people in Indiana should definitely thank this man, or else they might be celebrating pi on either March 2nd or March 20th. Now, I love this term, pi philology. It's a term that's used for creating techniques to memorize the digits of pi. Now, for those of you who were here last year, you'll remember that the current recognized by the Guinness World Records, the current record at that time was 67,890 digits, held by Lu Chao. Well, I can tell you that since then, that record has been broken. Here is the new record, 70,000 digits, recited by Rajveer Meena, and he recited 70,000 decimal places over the course of 9 hours and 27 minutes while wearing a blindfold. Now, of course, there were, I'm sure yesterday, with all the Pi Day events going on around the nation, there may have been some records broken, but this is the current standing as recognized by the Guinness Book of World Records. And now, before I conclude, I want to talk about, remember, on the first slide, I mentioned what is pi. And now I want to come back to it. I'm sure you guys saw that pi is used in a lot of places that don't relate to circles, or at least certainly don't seem to relate to circles. And something interesting is that many people would argue that pi should not be defined as the ratio of a circle's circumference to its diameter. So I was reading a very interesting article, and it was saying that basically, if you look at, for example, the term electricity, the Greek word for electricity is very similar to the Greek word for amber. And that is because in the first experiments in ancient Greece, when people noticed that there was this thing, the strange property of objects called electric charge, they were rubbing amber against certain objects and then realizing that certain strange things would happen. And so because of that, the term electricity became associated with the term for amber. However, nowadays, we would never call we would never define electricity as the ability for amber to do some weird stuff when it's rubbed against other objects. And so in the same way, some people believe that we should not be defining pi just by this circle definition, because someone argued that the definition is much more fundamental than that. So a lot of times in advanced math and science, pi actually is defined differently. It's defined as twice the smallest value, or the smallest positive value, x, such that cosine of x equals 0. And then you might say, well, isn't that definition a little circular? No pun intended. The reason is that the cosine function will also be redefined in terms of its Maclaurin series. So the cosine function can be defined as 1 minus x squared over 2 plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial, and so on. And so in that sense, you can create a consistent definition for pi. And another way of defining pi actually depends on this sort of fundamental natural exponential function. So for those of you who know calculus, if you look at that equation, the derivative of a function equals the function itself. That is one of the most important differential equations, and it gives rise to one of the most important classes of functions, the natural exponential, which we often say is e to the x, or a constant times e to the x. It turns out that the period of that function, so the value for which, if you added to the input, you would actually get the same value, it turns out to be 2 pi I, where I squared equals -1. And so in that sense, 2 pi I is this fundamental constant, because you see, f prime equals f doesn't have any numbers or units attached to it. So maybe you would expect, oh, the period should be something like 1, something very simple. But no, it ends up being the strange number 2 pi I. And then by dividing by 2i, then you get this number pi. And so that is arguably the perhaps more interesting or more fundamental way to define pi. And also that definition nets you both pi and e at once. So again, thank you so much for listening, and I hope you enjoy.